So good morning, good afternoon, good evening. Thank you all to attend this IEEE CASS Rio Grande do Sul talk. So good morning, good afternoon, good evening. Thank you all to attend. Sorry. Then today we have the pleasure here to have a Professor Sandip Kundu from University of Massachusetts Amherst. So thank you very much for accepting the invitation. And today we have also the pleasure to have as session chair Professor Felipe França from Federal University of Rio de Janeiro. So thank you both to accept our invitation. So Felipe, thank you again, and the floor is with you.
Thank you, Ricardo, for the invitation. Well, I hope I can be of any value here. Well, I'm happy and I'm honored to introduce you, Professor Sandip Kundu. He's a professor of electrical and computer engineering at the University of Massachusetts Amherst. Recently, he also served as a program director at the NSF, and Sandip began his career at IBM Research as a research staff member, then worked at Intel Corporation as a principal engineer before joining UMass Amherst as a professor in 2005. He has published nearly 300 research papers in VLSI design and test, holds several key patents, including ultra drowsy sleep molding processor, and he has given more than a dozen tutorials at various conferences. He's a fellow of the IEEE, fellow of the Japan Society for Promotion of Science, senior international scientist of the Chinese Academy of Science, and was a distinguished visitor of the IEEE Computer Society. He has served as associate editor of a number of IEEE and ACM journals. He has been the technical program chair, general chair of multiple conferences, including ICCD, ATS, ISVLSI, VFTS, and VLSI design. Well, Sandip, good to see you again.
Yep. And thank you, Felipe, for the kind introduction. And I will get started with the presentation. So my talk today is about improving reliability of DNN algorithms and accelerators. Before I start the presentation, I'd like to acknowledge the contribution of my students who worked on this project, specifically Bruno Goldstein from Federal University of Rio de Janeiro. The other collaborators include Alexandre Neri from University of Brasilia, and a student here, Vinay Patil, who has also contributed to some of the work. So the title of the presentation is that reliability across algorithms and the hardware accelerator. And I would like to emphasize that a reliability problem, it spans across the entire computation stack. And so I will expand that as I go through the presentation with some use cases that we have to address reliability at multiple levels and not just at one level. The reason for that is that the failure of electronic systems is fairly common. We have failures due to power supply outage, we have failures due to power supply glitches, we have failures due to long-term aging problem, we have failures due to cosmic rays, we have failures due to alpha particle strike, and so on and so forth. So what I'm going to do is go through a few of the use cases that are relevant to our presentation to emphasize that you cannot just solve the problem at one level and assume that everything is solved. And then we will do a deep dive into the specific presentation topic today, which is deep neural networks. And we'll be asking the question that how reliable are they? And if they're not reliable, what can you do about them? And look at some of the variants that we use today for optimization of deep neural networks, specifically with model compression, what does it mean for the overall system reliability? Present a solution related to DNN microarchitecture. Our emphasis is on achieving something which is ultra low cost and which solves a large part of the problem. So as I mentioned, that reliability problems happen across the computation stack. And you can think of, say, the internet as a prime example. In the network, we have data link, where we can have bits in the packets getting corrupted, which are typically corrected through ECC. We also have a network layer where some of the packets that you send may be getting lost, and we have to request retransmission, and we get those packets back. We have a session layer in networking where we can start a session, we can terminate a session, we can suspend a session, we can restart a session, and so on and so forth. And finally, we have the application layer. And if for some reason the connection dropped, we have abilities to deal with them. And exactly the same thing happens with DNN and its applications as they're used today. So I'll take an example which was in press for a long time, but not many of you might have looked at the details of the newspaper articles that came afterwards, explaining the reasons for the crashes. So around 2018, within a very short span of 4 months, we had 2 airline crashes involving Boeing 737 MAX. One was in Indonesia, and the other one was in Ethiopia. And upon investigation, they found that both of these crashes were caused by a single sensor malfunction. And of course, reliable systems should not have a single point of failure, and Boeing has been designing airplanes for a long time. It turns out that Boeing actually had redundant sensors, but the software just relied on output from only one of the sensors. And there have been various articles. Some claim that it was a paid option to have data from the second sensor as well, and some are not very clear about that. But whatever it is, we do know that there was a single sensor which caused the aircraft to crash. And if we go through a little bit of the background, so the 737 MAX is a longer version of 737. It holds almost twice the number of passengers, so naturally it needs a bigger engine. And this bigger engine, in some maneuvers, causes the aircraft to just pitch up. So specifically, the explanation that they offered is that the engine is at a forward position, and when the engine has large thrust, then the aircraft nose just tends to tip up. And they have built a system called maneuvering characteristic augmentation system, which is designed to overcome that, to keep the aircraft in the normal mode without intervention from the pilot. So it's supposed to be an autonomous system. And they achieve that by swiveling the horizontal tail, and they stabilize the whole thing. So if you look into the system that does this automatic adjustment, and it happens when the engine has a lot of thrust, there are 2 inputs that this system accepts. One is the angle of attack, which is the angle at which the plane is traveling, and the other is the g-force. So the angle of attack sensors, or the AOA vanes, are these 2 things that you can find in the nose of the plane. And in case of MCAS, the input was leveraging just one vane, and that is the one which happened to go wrong, and which made which caused MCAS to make a bad or wrong decision. pointing the nose towards the ground and cause the airlines to crash. And in those situations, it has been reported that the system overrode the pilot's input and just resulted in crash. So what can we learn from here? First thing we learn that all safety critical systems, airplanes, self-driving cars, they have to have sensor redundancy, because if we have wrong input and based on that, if we take wrong action, we're in trouble. So clearly, we have to make sure that we have a check that the input that you're receiving is correct, and we have that check only through redundancy. The second lesson, which is pretty much obvious, is that unless there is a failure, if you look at the system in the airplane, they're receiving identical inputs from the redundant sensors. And the third point, which is also somewhat obvious, is that most of the ML systems are trained with trace from the correct systems. So basically, you're training a machine learning system which is receiving two inputs that are identical in nature, and you're using an algorithm to build a model. You have no control over whether the algorithm is going to rely on one input or both inputs. So ML systems trained with trace from correct systems actually do not have the failure in the trace, and which can cause error. So next, I'm going to go through another use case, which is the Tesla use case. And again, the Tesla use case is what has been reported from the press. So of course, I have no insider information about Tesla, and I will just summarize what I have read from the trade press. That Tesla cars have an SOC to make the perception and the driving decisions, and there are the SOC has two processors. They also have redundant power supply, and they have different levels of redundancy in there. So the reason Tesla has in the SOC 2 processors is obvious, because you wouldn't want to have a single point of failure in the SOC. So normally what happens is both the chips are doing the same computation and making their own independent decisions about what the car should do. And then you have a validation check, which makes sure that the decisions are exactly matching coming out of the two processors, and they have different levels of redundancy in there. Okay, so here I'd like to draw some lessons. And some of the lessons are from the Tesla case that even if the hardware is capable of processing multiple streams, there has to be hardware redundancy. Because if you didn't have processor redundancy, you'll have a single point of failure, which is why they're incorporating two processors. And at the same time, the two processors are fed by two independent set of inputs. And these independent set of inputs, they're not completely identical, and there could be a partial overlap between the streams, which should result in more or less the same decision. But at the same time, because there's a partial overlap between the streams, which clearly speaks to data redundancy, you have opportunity for cross-validation. And what should happen in case of disagreement between these various perception systems? If you have disagreement between these perception systems, then of course, this autonomous driving mode should disengage, and the user should gain full control of the system. I will use another use case from a while ago, which has to do with IBM System 390 G5 microprocessor. In the G5 microprocessor, you had two identical CPUs, mirror units, and doing redundant execution. So you're executing the same thread on both of these CPUs, and the CPU and the IO are fully replicated, allowing you the opportunity for cross-validation. And this is the type of thing that you'd need in an ultra-reliable system. The lesson from the G5 is that G5 enables redundant execution, but interestingly, G5 also allows solo execution, which may be exploited to process independent streams in parallel. And that begs the question that must every execution be checked through redundancy at the hardware level? And the answer to that is that the context matters, and only at the system level can you decide whether to engage in redundant execution or not. So, some processing, you really care about speed, and with some other processing, you care about the correctness much more than just independently validating the streams. And we can see that in the case of operating systems, for example. If you're doing anything to do with page table, you would want to make sure that the threads executed correctly. But if it comes to execution at the application level and the application results in an error, then you can have the application crash and you can restart it without having to restart the operating system. So the context really matters when you're provisioning the redundancy to build a reliable system. The last case that I want to talk about are two recent papers which appeared in this year in the first quarter, one from Facebook and one from Google. The Facebook papers observed that there is a lot of silent data corruption that happens in the data centers. So mostly they looked at the workloads that are executing on machine learning systems. And these are inference systems, and they found that sometimes when they rerun the same program, then it might result in a different classification than the first run. And so that is a cause of concern, of course. And the paper from Google reported that in their data center, they find that some of the cores, there are thousands of cores in the data center, and they find that some of the cores produce errors while other cores do not. And so basically, they had to go and figure out which cores are source of errors and quarantine them within a data center. And given that in today's CPUs, they may integrate multiple cores, you may have a situation where you're not quarantining the entire CPU by itself, but you're just quarantining a core within the CPU, which makes the system level design somewhat more complicated. So the lessons from there is that some components are more likely to fail than others. And if failure prone and dependable components can be identified early, it helps in better decision making in terms of improving reliability of the system. And failure prone components may be replaced to improve the system health over a long period of time. So if you know that which are the weak components, you could just replace them with better components, and over a period of time, the system reliability may improve. So the lesson from here, in all the cases that we have seen, is that sometimes it's your application which is not doing things correctly, as was the case with the Boeing 737. And sometimes it may be the hardware itself which is not computing correctly, and you need to do something about that. And sometimes it is the input which is coming to the system that may be corrupted, and you may need to do something about that. So clearly, if you have a system which is based on a DNN or any other system, if you're asking the question, where is protection needed? The real answer is protection is needed at every level of the design. And designing a resilient system is really an exercise in choosing appropriate redundancy strategies across the entire computation stack. So you cannot really go overboard in putting lots of redundancy in one of those layers in the computing stack and ignore putting in redundancies in other layers, that will not make the system reliable, and that will also not make the system cost proportional, which is the key message that I'd like to point out. So when you're making investment, which involves a cost, such as adding redundancy, it should have some proportionality across all levels, because you don't want to make any individual level overly secure while some other layer in your computing stack is not so secure. So the problem that we are going to look at is specifically you're zooming down. And in this talk, I'm going to be talking about microarchitecture, which is the subject here. And specifically, we are looking at deep neural network models. And deep neural network models are used heavily in computer vision. They're used in safety critical systems such as autonomous driving. And what our goal is to analyze that how reliable are deep neural network models in terms of computation. We have seen report from Facebook, as I've just shared with you, that during the computation, they've observed that DNNs produce a lot of wrong classifications due to errors. And if we have to protect the classification to make sure that the system remains reliable, what can we do to make a DNN system more secure? So in other words, how can we detect errors when they happen? And when we detect such errors, how can we mitigate those errors? And of course, the solution has to be fairly lightweight to have any practical usage or applications. So we are looking at deep neural networks, and in this particular case, in the deep neural network, we have an input and an output, and it goes through multiple layers of convolutional layers and also fully connected layers. So after it goes through convolutional layers and fully connected layers, it outputs some probability of a class. So for example, in this particular example, you're looking at the input is a dog, and you know at the end, if it's classified correctly, you'll have a higher probability associated with it of being a dog, and lower probability for all these other classes. So how does the computation work? In the convolution layer, we have an input, which at the first layer, like convolution layer 1, the input is directly an image. And on the image, we apply a filter. This filter is scanned across horizontally and vertically through this layer. And by running a convolution, we compute a single value, and which then is passed through a nonlinear function, and we create an activation map. But let's just ignore the nonlinear function for now. We are performing convolution, and we just stored that in this output layer. And in case of a fully connected layer, which is FC1 and FC2 that you're looking at, we have the inputs, which is in the form of a matrix, and we multiply that with weights, and we end up with outputs. And so there are lots of cross connections between the inputs and the output via the weights, and it's a highly densely specified matrix. So convolution and fully connected layers account for more than 90% of the overall computation in a deep neural network, and it dominates the runtime and the energy consumption. And so if you're going to spend 90% of the time doing something, if errors happen, it's likely that it will affect that 90% of your computation more than the other 10% that you're doing. So our goal is really how to make that computation more reliable. Okay, so next we are going to be talking about an analysis that we have done on compressed DNN models. So a typical DNN model, it goes through compression, And the objective of the compression is to reduce the amount of the computation that you're going to do. So focusing on that 90%, we are really trying to cut down the amount of the computation that you're going to do. And we have a couple of ways of doing that. One is taking a dense network and then pruning some edges and nodes to create a more sparse network so that we do less of a computation. And the other work that is typically done is making the computation itself simpler by moving from floating point computation to integer computation. So how does it work? In the pruning process, we start with a dense network, and then we find that in this network, the weights which are associated with some of these edges may be fairly low and very close to zero, in fact. And so we can start deleting some of those edges. And once we delete those edges, then we measure what happened to the classification accuracy. And if the classification accuracy drops, then you go back and we use the standard backpropagation algorithm, and we fine-tune the weights again, and so that we improve the classification accuracy. And this is done iteratively so that you end up with a network which is highly pruned. So one of the questions that naturally occurs to us is that if you're thinking about a reliable system, then is a dense network better than a pruned network? Because clearly, in a dense network, there are a lot of connections, and if some of those connections fail, perhaps it's not such a bad thing. Perhaps your classification will not have error. And in pruned network, each edge and each node is highly significant because if you don't have them, it's going to introduce classification error. So perhaps if any error happens in the computation with these nodes and edges, it will make the system more unreliable. And we don't know that answer until you do the experiments. And so that's what we would like to investigate. The second optimization which is done with this deep neural networks is quantization of the values. So with floating point number, you have a whole range of precision that you can achieve, and these are finely quantized values. But we can scale down the number of bits, and we can go from 32-bit floating point number to a fixed point number. And while we are exploring the fixed point number, we can explore 16-bit integer values, 8-bit integer values, and we could even go down to 4-bit integer values. What is observed is that when you go through the quantization, quite frequently, that in terms of classification, we do not see any loss in accuracy. And so, which really means that no retraining is needed when you go through this quantization of this network, unlike the other case that you have seen with the pruning. And this simplifies the computation quite a bit. But just like the previous case, we'd like to know what does it do in terms of reliability, because if you have quantized values and if a bit changes, then perhaps it can shift the values around a little bit more. And does it introduce more classification inaccuracy? And that's the question that we'll be asking ourselves. So the research questions are, how reliable are compressed models against faults? And does pruning increase the exposure of the most relevant weights? And does data quantization make the model more reliable or less reliable against faults? So we are going to be evaluating what happens when you introduce bit errors into 32-bit floating point number versus 16-bit integer number versus 8-bit integer number. Okay, so now on to reliability analysis. So in order to do reliability analysis, we had to build a tool which will perform the fault injection and rerun the classification and then figure out whether the fault causes misclassification or not. Okay. So this tool was developed by Bruno Goldstein, and it's available in GitHub page to anyone who wants to use the tool. And specifically in this tool, we consider transient faults. So transient faults, they last for a very short duration. They just flip a single bit, at a random location and at a random time, and as a result of which maybe errors can happen. And you'd like to know what happens in terms of classification error as these errors occur, and perhaps we can then also change the rate at which the errors happen to see if it has any impact in terms of classification. So the evaluation methodology is that when we inject an error, there's a golden response without the error, and then there's a faulty response with the error. And you're looking at, in terms of classification, the top one result, whether that result changes or not. And we perform three types of analysis. One is we vary the, which bit is faulted. So it goes from least significant bit to most significant bit, and we see what happens as a result of changing those bit positions. We do it per layer. So, if an error happens in convolution layer 1, then do we have the same impact if we have in convolution layer n, for example? And we study the overall reliability. The reason we do that is if we find a differential, perhaps in terms of building a reliable solution, we can have a different solution for convolution layer 1 than a solution for convolution layer 5. So we have to know their contribution to the overall reliability of the system at the final classification level based on their location and the bit positions. So in the experimental setup, we considered the following networks. We considered AlexNet with 8 layers total, ResNet 18 with 18 layers, ResNet 50 with 50 layers. And the post-training quantization, we consider going from 32-bit floating point number to 16-bit floating point number, and 32-bit to 8-bit integer. And when we did the pruning, we found the following pruning nets, like AlexNet was pruned quite a bit, 88.31%, ResNet 18, 59.92%, and ResNet 50, we had different levels of pruning. The study was conducted, and the data set that we used is ImageNet 2012, which is a fairly large set of data. And here are the results. So what we observe is that the first result has to do with quantization. So let us say that we didn't do anything with the quantization. We are just starting with a 32-bit floating point number. And if you have bit flips in various bit positions, then what is the probability that you're going to have misclassification, which is what we call silent data corruption, or an error. And as you can see, that in the floating point, 32-bit floating point number, the results look like this, that an error in the 30th bit position is more likely to cause a classification error than any one of these bit positions. Now, if you do know something about the 32-bit floating point number, the bit 31 is the sign bit. And so what it is telling us is if the sign bit of the number goes from changes from a positive number to a negative number, or vice versa, it has less of an impact on classification than bit number 30. So why would that be the case? And what we did observe informally is that most of the weights tend to have values that are pretty close to 0. These are small values. So clearly, if there are small values, if you change the sign, the contribution is relatively small. However, when you look at the bit number 30 position, and in this 32-bit floating point number, this happens to be the MSB for the exponent of the number. And in 32-bit IEEE standard floating point number, which uses XS127 notation, so if this bit flipped, it basically the exponent of the number just went up very, very significant. As I mentioned, that most of these numbers, they have small values, so this exponent is more likely to be 0. And when you flip that, it's more likely to be going into 1, and which is just amplifying the exponent significantly. And it's the changing the magnitude of the number the most. And this is what we find causes the most error in the in terms of which bit position contributes to most classification error. Now, switching to a 16-bit integer, what we find is the MSB, as expected, leads to the highest rate of misclassification, followed by the next bit, 14th bit, and followed by the next MSB, and so on and so forth. So by the time you are looking at flipping the bit position 0 through 7, you find it has almost no impact in terms of classification error. And I want you to make that observation because we are going to be relying on this property later on when you build our solution for error detection and error mitigation. So this is just an analysis which is telling us that if you have an error in bit position 0 through 7, it has almost no impact on the classification error. That is not the case when you switch to integer 8. When you switch to integer 8, then it appears that every bit flip actually leads to fairly a significant amount of classification error or silent data corruption, and which basically means that if you're starting with integer 8, then we have to somehow think of how to protect every bit if you're building a more robust solution. Now we are looking at quantization effects layer by layer. So if you follow along the x-axis, the layer level is increasing. If you look at a silent data corruption with a 32-bit floating point number, which is the purple line, it follows the pattern like that on the top for AlexNet, and then we see for the ResNet 18, and then we see for ResNet 50, and similarly for SDC, the top one for 16-bit integer, and SDC for 8-bit integer for AlexNet, ResNet 18 and 50. What we observe is that that the initial layers contribute most to misclassification. So if you have error in the subsequent layers, the impact is not as much as in the initial layers. We also find that if you go from 32-bit floating point number to 16-bit integer number, then the misclassification reduces by 27x. And this is somewhat unintuitive because you're starting with full spectrum of values, you're going down to a quantized spectrum of values, but you're actually making the system more robust in the process. Now, here is a slide that's summarizing the results for pruning. And again, pruning on a layer by layer basis. So the purple line, just like before, is the 32-bit floating point number and the original one. And then the orange line is 32-bit pruned. And the next line is 32-bit pruned with 30% of the faults. And then there's silent data corruption reduction. So I ought to explain what each one of the lines is. So let's assume that your basic underlying hardware has a certain rate of error for each and every computing unit in the design. For each and every gate, it has some error rate. So if you prune the model, and if you inject the same number of faults into the network as the original model, you are basically saying that the prune network has a higher fault injection rate than the original model. So that's not right, and that is the orange number. And the next line the color, the cyan, or the bluish color you're looking at, as we prune the network, so we also reduce the number of fault injection in proportion to the reduction in the network size, and therefore we inject fewer number of faults, and then we find that the system is reliability has improved with pruning. So in this case, we can establish an upper bound, which is really coming from this orange line, and we can have a lower bound, which is really coming from this blue line. And we find that up to a 9x reduction when we do the pruning. And here are the results a little bit more in detail. So we are looking at the results here for AlexNet, ResNet 18, ResNet 50, and for each one of them, we're looking at original and the pruned version. And we find that the pruned version always has higher reliability and lower rate of error than the original version. And this study was done both for top 1 classification and top 5 classification, so which is what you're looking at, SDC at top 1 and SDC at top 5. And so that's the summary of the result. What I'd like to draw your attention to is that pruning almost always is improving the reliability, but going into 8-bit integer is not necessarily improving reliability in the prune network. The 16-bit is always improving reliability of the prune network, but going into 8-bit is making it worse. So by doing pruning and quantization, we find that the final classification actually improves by almost 110x. And what we found then, the model compression provides more resilience to the system. In summary, if you think about it, if you do pruning of the net, if you do less computation, you're less likely to have error. And that's one-line summary that we've observed from running this simulation. Pruning reduces the model size and the computation time, and which reduces the exposure of the application to the faults. And aggressive quantization, like going into integer 8-bit, you should be careful, because what we found is that it actually increases the error propagation by 22.5-fold or 23-fold almost when compared to 16-bit integer. So looks like pruning the network is the way to go in terms of improving reliability, and moving to 16-bit integer actually is beneficial. So having observed that going to 16-bit integer actually makes the system more reliable, we are going to be riding on that and going to the next part of the presentation. Is the first part was just analysis, what happens to classification. The second part is design. How can we detect those errors when they happen, and how can we mitigate those errors by adding the least amount of hardware? So we are looking at resource-constrained devices, and it's also equally true for resource-rich devices, because nobody really likes to add things if you don't have to. So can you provide a low-cost application-based detection capability? And after detection, how can you mitigate error without using complex hardware? So the solution that we look at is low-cost arithmetic code. And that's because neural network operations, as we have seen, multiply and add constitute like 90% of the operation. And arithmetic codes are known to protect the multiplication and the addition, in the sense that if an error happens, they're known to detect most of them. So there are other solutions also possible. And one of those solutions is known as recomputation with shifted operands. So let's look at how this will work. So suppose I do an example. I multiply 3 times 5, I get an answer 15. And I have only one multiplier. I'd like to know whether this answer 15 is correct or not. And given that I only have one multiplier, how can I do that? So one thing I can do is I can left shift the number 3. So 3 is 0, 1, 1. If I left shift, it becomes 1, 1, 0. And I can also left shift the number 5. And so 5 is 1, 0, 1. And when I left shift it, it becomes 10. And then using the same multiplier that I used previously to compute 15, I can multiply 6 times 5. I get 30, and then I right shift the number. And if it matches my old computation, then I say that I got I got good result. And if it doesn't match, like if 3 times 5 become 14, and then I multiplied 6 times 5, and if it didn't become 28, which is very unlikely if you had an error that it will do that, then by right shifting we find a discrepancy between the results, and we detect an error. So this solution is very good when you have a limited amount of hardware resource, but you can afford to spend time by doing this computation, which would mean that you have no hardware redundancy, but you have time redundancy. So you can afford to recompute. But the cost in this case is 2 times. You're doing the operation twice, the shift operation, and you're doing the multiplication twice. Another solution, which is known as residue code, which is based on Chinese remainder theorem. What you do is you suppose you have 2 numbers, z and y, and you compute the residue with respect to some typically a prime number, but not necessarily so, some number a, and z plus y modulo a is expected to be the same as z modulo a plus y modulo a. The whole thing, the modulo a is taken again. And exactly the same property holds when you do the multiplication. But in order to implement the residue code, you will need you'll need an adder for computing the modulo, and then you'll need the error detection circuitry. So that's like the added cost. The solution that we are preferring is arithmetic AN code. So in arithmetic AN code, what happens is if you want to do addition of z plus y, we pre-multiply z with a, which is typically a prime number, and y with a, and then we obtain the result. And our check is that this number is divisible by a. And if it is divisible by a, then we have verified that it computed correctly, and we also have the correct result. If not, we detect an error. So how much does it cost to implement arithmetic AN code? So that's in the next slide. So let's look at a convolutional loop in a fully connected, in a convolutional layer, what it looks like. It looks like a loop like this for filter in 0 to number of filters, for channel in 0 to number of input channels, for output height for every output weight, and for every kernel height and for every kernel width. Then you do this MAC operation, which stands for multiply and accumulate, and this is that computation in the fully connected layer. So in terms of order of computation in convolution, it turns out the order of computation is number of filters times number of input channels times output height, output width, kernel height, kernel width. So that's the overhead for normal convolution operation. And now with our modified AN code, what we are doing is we are pre-multiplying the inputs with some value A. And after we are done with convolution, we are post-checking the result to make sure that it's divisible by A, and we obtain the final result by dividing by A. So the overhead for doing that is to pre-multiply the input, we have to do input channels times input height times input width. And for post-verification, we have number of filters times output height times output width. Notice that the first order of computation has 6 multiplications, and this one has 3 multiplications. So as you can see, the order of computation goes down significantly for this checking operation. And the checking overhead, if you have a 7 by 7 filter, it's somewhere around 2%. The overhead for checking the correctness of the result is about 2% if you have a 7x7 filter size. And even that 2% is only in terms of number of computation, but in terms of computational effort, it's even less. So let's look at that. So suppose we choose a equal to 7, and when you do the pre-multiplication, we know that 7 times any number n is same as 8 minus 1 times that number n, which is 8 times n minus n. And this really is 8 times the number is really shifted by 3-bit positions and then perform a subtraction. So the cost of this multiplication is really the same as cost of an addition or a subtraction. That's it. And similarly, if you choose this a equal to 7, and if you do the division, or if you do a modulus operation to check whether it is correct or not, we can, given that there is a 7-bit value a, like 7-bit is, the number 7 corresponds to 3 bits of a, and z, suppose, is a 32-bit number, so we can group the number z in groups of 3 bits. So z0 is 3 bits, z1 is adjacent 3 bits, z2 is the next 3 bits, and so on. So this number z can be rewritten as z0 plus z1 times 8 plus z2 times 8 squared plus z3 times 8 cube, etc., modulo a. And this, if you do this operation, z1 times 8 modulo a is same as z1 modulo a times 8 modulo a, but because a equal to 7, it becomes same as z1 modulo a. And same thing goes for 8 squared. 8 squared is 64. So 64 modulo 7 is also a. And 8 cube is 512. And if you divide 512 by 7, so 7 times 73 is 511. So modulo a 512 is also 1. So it really simplifies. And then it just becomes this. If you build an adder tree, the final result is just 3 bits. So it turns out that even though we are doing multiplication and division, if you choose this a value appropriately, we can just convert the multiplication and the division operation into just an addition operation, which is extremely low cost. So our approach is use a value of a, which is like 2 raised to the power p minus 1, where p is a prime number. If p is a prime number, then a is guaranteed to be a prime number. It's called the prime Mersenne number. So, for example, if you choose p equal to 3, 2 raised to the power 3 minus 1, a is 7 is a prime number. If you choose p equal to 5, 2 raised to the power 5 is 32 minus 1, 31 is a prime number. So these are the Mersenne primes. And if you use Mersenne primes, then the computation of multiplication and division is extremely simple, as you have just seen in the previous slide. And the resulting data is divisible by a, and which is fairly easy to check. And that's exactly what you're going to do. Now, this solution is going to be a completely overhead-free solution, because we made an observation that when you use 16-bit integers, then any error in the lower bits does not cause classification errors, which basically means we can just zero out the lower bits or put any value. It doesn't matter. It's not going to lead to the classification error. So therefore, we use 5 bits to do ECC over the weights, and it makes sure that the weight that we are receiving is completely protected and can be checked by ECC, and plus n number of bits for input data, and n is only 3 and n is 5 if a equal to 31. And we observe that on a 16-bit integer, the lower 7 or 8 bits, any error did not really matter. So we are using those lower bits to actually implement error correcting code, and also to the overhead for a, and without increasing the size of the data. So we ran our experiments with this to see if you implement arithmetic encode and if you do random fault injection, what fraction of the faults that we will be able to catch. And then, of course, you have to answer the question that how are you going to correct those errors? Now, if you look at our benchmark circuits, we target LANET 4, convolutional network, AlexNet, VGG16, ResNet 18, and we do that for we listed the corresponding model accuracies that we are looking at. So as you can see that in the LANet 4, when you go into 16-bit integer, we get 99.14% accuracy. And when you go into 11-bit integer, then we still have 99.14% accuracy. And the next example, the accuracy just drops just a little, and sometimes it may even improve. And that's, it's really at the margin that you're looking at. The total number of weights are something like this, up to 25.5 million weights, and total number of max or multiply and accumulate operations, they go up to 3.9 billion from 36.2 million. And we ran experiments with various fault injection rates from 10 to the power minus 6. And so, 1 bit will be impacted by error out of every million bits to fault injection error of 10 to the power minus 1. And we study how are we able, how many of those errors are we able to detect and how many errors are we able to correct. And I have not spoken about the correction part, which is coming up. So here in this slide, we have the results. On the left-hand side, you have the results for LANet, Convolutional Net, AlexNet. And then in the next column, you have VG16, ResNet 18, and ResNet 50. And for each one of them, we have you have computed the error detection for bit error rate of 10 to the power minus 2 and bit error rate of 10 to the power minus 1. And we just plotted them. The quick summary of the result is that if you use A equal to 7, we are able to detect more than 98.5% of the errors, which is a pretty high error detection rate, given that we are multiplying the number with 7 and we still manage to fit everything into that 16 bits of data that we originally had. We didn't really increase the data width. So without increasing the data width, we did not sacrifice the classification accuracy, and we also achieved fairly high fault coverage. When you look at the impact of, what impact the value A has over ResNet 50, and we experimented with various values of A, like A equal to 7, 11, 13, all the way up to A equal to 31. Note that not all of them are Marcian prime numbers, but here we just wanted to study the impact of A. And what you're looking at is classification error. And if you had no checker, we see that on the right-hand side figure that we are going to have very high rate of error, classification error going up to 100% when the bit error rate goes above 10 to the power minus 3. But when you use A equal to 7, which is the red line, and what we have done here is when A equal to 7, we detect the error, and once the error is detected, we simply say that we don't know what the correct value is, but we have detected an error. We are going to change the value to a 0. And that's our error correction methodology in this particular slide. And when you do that, we find that this strategy works very well for error rates of 10 to the power minus 6 to error rate of 10 to the power minus 3. So up until that point, the strategy of detecting the error, and simply if we detect an error, we don't know how to correct it because we haven't provisioned enough redundancy for correction, but we just change the value to 0, which is the most common value, or closer to the most common value in any kind of trained network. Then we find that it has almost no impact on classification error. Whereas if we didn't do that, then we could have classification error pretty close to 100%, as you're looking at from the chart here. So in terms of error mitigation, we perform some additional experiments. Suppose we don't detect any error, we don't correct anything, then what happens? And suppose we detect an error and then we just mask the error by setting the result to 0, then what happens? And the oracle is, if errors are detected, we set it to the expected output, and then what happens? So what we find is that if you didn't do anything, we can have a fairly high classification errors in all of these examples, except the smallest one like LANET or something like that. The classification errors for the bigger ones is approaching 100%. If you do the masking, and if you do the masking with A equal to 7 versus A equal to 31, then we find that there's a small difference, but both are working equally well, which basically tell us that A equal to 7 is probably good enough for most of the situation. And if you use the oracle, then we find the result from the oracle is not much better than simply replacing it with 0. So we find that if you implement the scheme, there is no accuracy degradation up to 10 to the power minus 3 bit error rate. And, so we are able to detect greater than 98.5% of the multiply and accumulate errors, no accuracy degradation up to 10 to the power minus 3 bit error rate, and marginal accuracy drop in 10 to the power minus 2 error rate. Going anything above that is really stressing the system, and we don't anticipate that in any real life circuits. So no increase on the size of the current data path. So we didn't really increase the size of the current data path. And we leverage the fact that after quantization, some bits are insensitive to errors. And by observing that, we take advantage of them to protect the circuit. So in conclusion, reliability must be considered proportionally at all levels. This is the main point that you want to make. Pruning and quantization have an impact on the overall reliability of the DNNs. AN code provides a lightweight fault detection capability for DNN systems, and it can either be implemented at application or microarchitectural levels. It can even be a lighter and end-to-end solution. And we are working on a solution which is going to be even lighter weight than this, and it'll be published in a future date. This particular paper, set of papers that you described, they're already published in conferences. So that's what the scope of this talk is. Thank you for attending the presentation, and now I'll be able to entertain your questions.
Okay. Thank you very much, Sandip, for your talk. I have a question for myself, on my own, and it's about the circuit implementation. How far are we from that for checking this in terms of circuit costs, etc.?
So in terms of implementation, as I have shown in one of the earlier slides, that really the multiplication and the division operations are just simple adders. And in terms of implementation, it's just really not so much of the data path, but the control circuit to schedule the operation is where we'll have to spend the effort. We haven't really done it, but we don't expect the overhead to be more than less than 1%.
Well, thank you. Well, Ricardo has a question for you. Dear Sandip, you presented some reliability problems in the Boeing 737 MAX. Do you have some information about the reliability related to radiation effects?
No, I don't. Whatever results I reported related to that particular system problem, it comes from a newspaper and other news sources that are already published. So I have no insider information.
Okay, thank you. Well, Danielle, I don't know from where Danielle is, has asked about Does A equals 7 mean 7 bits are reserved for ECC in each integer 16-bit word?
No. So we multiply with an integer value of 7, which means that in terms of bit, we require 3 bits. So which means that when you're training the network, we train the network with not 16 bits, but something like, so one potential is 16 minus 3 or 13 bits.
Okay. Okay, any more questions? Well, that's nice. Anything you could add, Sandip, about further work?
It's work in progress, and hopefully it'll be published soon, and so stay tuned.
Okay, thank you very much, Sandip. Ricardo, do you want to get in with us here?
Yes, so, well, people are a little bit ashamed today, so we have no more questions. So if somebody still have a question, please do it now. Yeah, but about the question I have done to you, Sandip, when we see that they didn't take care about some simple issues as doing the duplication of the sensor in the Boeing, so we put ourselves the question if they have considered also the radiation effects in their airplane. No, that is something that is more and more important nowadays with the reduction of the technology nodes that are more sensitive. No?
Yeah.
Well, okay, so thank you very much, you all. Thank you again, Philippe, for sharing the session, and Sandip for the very nice talk. And I see you next Friday. And then now you have the several hours to prepare your poster to the CASS workshop. Bye-bye. Have a nice weekend.
Bye.